Trust me, trust me, bro. That's funny. All right. So let's go on with the finish up chapter 3, which talks about isomorphisms and homomorphisms. And we will come back to this particular topic several times as we go along. I didn't know if I really wanted to talk about this particular section next or wait till later. Decided to go ahead and do it now and then revisit it at least 3 more times as we go through the semester. So we'll figure it out as we go. All right. So if you know your Greek roots at all, morph is structure-ish. And then iso, it means same. Homo means kind of similar idea. So the isomorphism, what we'll talk about to start with, that's same structure is literally what it means. Okay. So what do we mean by that? All right. So let's say we had, this is actually, I think, one of the ones in the book. Yes, this is actually the first problem on page, I just lost the page number, 80. All right. So let's consider R to be the ring Z6 and S to be the ring Z2 cross Z3. So let's see if we can create our addition and multiplication tables for each of these rings. Let's do the addition tables first, compare them, and then we'll do the multiplication tables and compare them. So again, our elements in Z6 are 0, 1, 2, 3, 4, and 5. And to save time, I'll just go ahead and fill this out quickly. You're all familiar with how addition and multiplication works modulo 6. There's a nice little pattern, obviously, right? We're filling out that particular table. We're going to investigate actually that pattern later on in the semester when we actually start talking about groups in particular. All right. So for the other one, I'm actually going to do this as far as this goes in a specific order when I label my elements. Now, of course, usually we put the additive identity first anyway. Let's put what would be the multiplicative identity next. One thing to notice about this particular additive group that we just formed, notice that when I add 1 to itself over and over again, I basically generate the entire group, right? Or the entire addition table. Sorry, I said group. We haven't talked about groups yet. But I generate the whole thing, right? 1 plus 1 gives me 2. Add another one, I get 3. Add another one, I get 4. Add another one, I get 5. Add another one, I get 0, right? I can generate everything in the entire addition table just by taking 1 and adding it to itself over and over again. I can do the same thing with 5. If I add 5 to itself, I get 4. Add another 5, I'll get 3, 2, 1, 0. If you try to do the same thing with 2, 3, and 4, it won't work. 2 plus 2 is 4. 4 plus 2 is 0. And then I just start running around again. Same thing will happen with 3 and 4. So anyway, that's something to notice that we'll notice later on in the semester. Also notice that 1 and 5 are relatively prime to 6. Another thing that will pop up later. Anyway, where was I going with that? Okay, the reason why I put the multiplicative identity here, remember the multiplicative identity for your Cartesian product is identity in the first, identity in the second together, right? And that gives you the multiplicative identity for the direct product, the Cartesian product. Let's start doing the exact same thing with the 1, 1 and see what happens. So if I add 1, 1 to itself, what do we get? 0, I'll get 0, 2, right? So let's write that element next, and then we'll fill out the the addition table. I'm just trying to show you why I'm putting them in this order. Okay. If I add 1, 1 to that, what do we get? 1, 0, good. If we add 1, 1 to that, we get 0, 1. And then again, we'll get 1, 2. And if we add 1, 1 to that, we'll get back to 0, 0. Right? So putting these in our table. Oops. This is addition table again. So 0, 0 added to anything will just give me back that element. We just figured out how to fill out the next row because we filled out the top of the table. It seriously is just in this room that it doesn't want to communicate with the pen to erase. Why are you not erasing? Grief. Now it's erasing. Thanks. Don't know why it's doing that. Goodness. All right, so we know if we go across that row, those are the elements that we'll get because that was exactly how we decided to generate our labels. And there's a reason why I did it that way. Okay. Ordinarily, I probably wouldn't have put them in that order, right? I probably would have done like 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, or something like that when I was creating the table, right? Just to try to be a little bit more systematic about how the direct product worked. If we do the next one, we should get 0, 2. 0, 2 plus 1, 1 gives us 1, 0. 0, 2 plus 0, 2 will give us what do I get there? 0, 1. And then we'll get a 1, 2 and a 0, 0 and a 1, 1. And if you start looking at the pattern, notice that the pattern over here was kind of these things got shifted. If you think of looking at a particular element, it looks like it kind of gets shifted down into the left for each row. And then rotates around. Notice the same thing starting to happen over here. So we would get, should get 1, 0, 0, 1, 1, 2, 0, 0, 1, 1, 0, 2 in the next row. 0, 1, 1, 2, 0, 0, 1, 1, 0, 2, 1, 0. Then finally 1, 2, 0, 0, 1, 1, 0, 2, 1, 0, and 0, 1. Phew, that was a lot of work. A lot of writing. We still have to do the multiplication table. Okay. This is why we're not going to do this way every single time. Okay. All right. But anyway, let's look at this table to start with, because this is the whole point of this section. Again, the title of the section is Isomorphisms and Homomorphisms. Right now we're working on the isomorphism part. We're looking on the same structure part. So the idea here is that, do you see an idea? I purposely did it this way. But do you see an identification that basically if I just change the labels, I see the exact same table? Right? So if I labeled these A, B, C, D, E, F, I could also label these A, B, C, D, E, F, and I would have the exact same table in both cases, right? So that's what we mean by same structure, at least informally. That if I write down the addition table, they're identical, just with renaming. Okay. Now, that was why I specifically put it in this order, because it might have been the case that if I put it in a different order, I might not see that structure right away. Okay. But If I can rearrange one table so that the structure looks identical, then we say that they are isomorphic. Now, for isomorphic rings, I still need to show that multiplication is the same way as well. Okay. Right now, what we have is an isomorphism of groups. Group is one operation. Ring has two. So, like I said, we'll talk more about groups later. Right now, these are isomorphic as groups. They may or may not be isomorphic as rings. And we'll see some properties that have to be true in order to be isomorphic as rings, and we'll see why later on. When we revisit this topic with groups, we might be like, oh, okay, I understand why it can be one but not the other. Okay. All right. Anyway, to do the same idea, we also need the multiplication table. So let me do that down here. And just again, to try to save some time, we'll do this quickly. If you do your multiplication table, that should work out that way. You should get, obviously, 0 times anything should be 0. Well, 1's the multiplicative identity, so you just have 0, 1, 2, 3, 4, 5 across that row. Notice there's some similarities between the 2 and the 4. And 3 is kind of its own little entity, if you will. And then 5 is kind of the reverse of the 1, except for the 0 part. All right. Doing this with the other ring, again, if I take the 0 times anything, I get 0, or 0, 0 in this case. We've already established that the 1, 1 is the multiplicative identity. So basically, I should just be rewriting the top of the table over again. When we take the 0, 2 through, we would get 0, 2. 0, 2 times 0, 2 would give me 0, 1 in this case, right? Because we're doing everything mod 3 in the second component. And then get 0, 0 in that fourth one. And 0, 2 and 0, 1 again. Run the 1, 0 through. We'll get 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0 again. The next row goes 0, 0, 0, 1, 0, 2, and then repeats. Final row should go 1, 2, 0, 1, 1, 0, 0, 2, and 1, 1. I know I did that quickly because the point isn't, can you do the computations? Because I'm confident you can all do the computations. You've shown me that you can do the computations. Okay. The point is to, again, look at the structure. So again, if I think about calling each of these A, B, C, D, E, F, and do the same thing over here, A, B, C, D, E, F, do I see the exact same table in both cases? Well, yeah, so again, this looks like A, B, C, D, E, F in that second row. That's what you would have here, right? This one is A, C, E, A, C, E. If we think about, again, replacing with those letters, and I get the exact same pattern, right? Notice the 2 is in this third column here. The 0, 2 is in the third column here. The 4 is in the fifth column. The 0, 1 is in the fifth column. So again, if I just rename them all the same thing, I see the exact same table. Right? This went 0, 2, 4, 0, 2, 4. This did the exact same thing. This was a relabel. You see what I mean by that, by the way? Is that okay? All right. So this tells us that these rings really are essentially, from an algebraic perspective, the same thing. They may look different, but they're literally the same thing. Okay? So we say in this case that Z6 and Z2 cross Z3 are, bless you. My goodness. There was something in 323 the other day because I was teaching college algebra in there and about 8 of us all sneezed in there. All right. So again, informally, isomorphic means same addition tables, same multiplication tables, if we call the elements the same thing. We need to make that a little bit more formal, right? So really, notice what I'm saying is I'm making an identification, essentially, right? I said if I called 0, 1, 2, 3, 4, 5, A, B, C, D, E, F, then I could also call my 0, 0, 1, 1, 0, 2, and so on, A, B, C, D, E, F. Really what I'm doing is I'm making a mapping, a function, from one spot to the other spot, right? So as a definition, we say that rings R and S are isomorphic if there exists a function. The book uses an F a lot for functions, but usually in algebra we like to use Greek letters for things that are homomorphisms or isomorphisms. So I'm going to use a Greek letter phi. I don't care whatever you call it. Faux, fum. Doesn't matter. I say phi because it's how I learned it. It was interesting. This is off topic. Took my niece to a children's museum a few weeks ago. And they had different Greek letter things. There's a whole sorts of different exhibits, right? But one of the things they had with Greek letters had pronouncing different Greek letters. It pronounced pi as p to go with phi and all that. So chi got key, and it was really weird. Psi was c. It was really weird, but it was all an e sound at the end.
I mean, I guess.
Sure, I don't know.
I don't know phonetics in Greek.
Yeah, I don't either. So, but anyway, I learned it as phi. So we got phi. You probably have drawn the zero with a zero with a line through it kind of thing, but I'm lazy. That's why it looks like a little loopy thing when I do it. Mine kind of looks like a row the way I just drew that one too. But yeah. Anyway, that was just a side note. I just thought it was interesting because I'd never heard it pronounced P before. So anyway, there's a function from R to S that has to satisfy three things, basically. Oops. I didn't want to write such. That satisfies. What has to happen? Well, there's three things. Actually, technically there's four. Because first we have to have a function. So I need to make sure we have a well-defined function. But what has to happen? Well, I said I had to call the first one in this example A, B, C, D, E, F. I also call the other one A, B, C, D, E, F. I need a mapping that is 1 to 1, right? I don't want to take A and B and both call them A on the other one, right? Okay. So the first one says that phi is 1 to 1. Of course, we can't just say 1 to 1. We have to use a fancy word in algebra. Actually, we have two fancy words. As a function, we say phi is injective.
What's the other fancy word?
Well, we need to satisfy 3 to make a fancy word. So I'll tell you what the fancy word is in a minute. Okay. There is another fancy word. It has the word morphism in it. Okay. Anyway, so if I say injective, I mean 1-to-1. Good. 2. Well, not only did I say I needed to have my A, B, C, D, E, F, I can't have my A and my B go to the same thing. If I have A, B, C, D, E, F in the first one, to have a table that looks the same, in the second one, I would need to see A, B, C, D, E, F again, right? I need to have the same number of elements in the other one. In particular, I need to make sure it's onto. Oh, I guess there is a third fancy word that I'll talk about as well, besides those two. All right, so it needs to be injective and surjective. When you put injective and surjective together, these two together as a word is bijective. Because it has both jectives.
Remember that for the test
Yeah. So injective, 1-to-1, surjective, onto, bijective, both 1-to-1 and onto. All right. But it's not going to be enough to make it 1-to-1 and onto. And here's what I mean. I'm going to draw this on the board rather than write it on the screen. But here's what I mean by that. So let me take a smaller example. I don't expect you to write this down. Let's just do an addition table real quick for Z4. Generate just like we just did for Z6, right? Okay. If I did Z2 cross Z2, what are the elements of Z2 cross Z2? Yeah, I got Z0, 0, and 1, so I have 0, 0. What else do we have? 1, 1, sure, do that way. What else? 0, 1, and 1, 0. Now again, I'm doing this under addition. And in particular, let's just look at the diagonal. If I add 0, 0 to 0 to 0, 0, I get 0, 0 again, right? If I add 1, 1 to 1, 1, what do we get? 0, 0, right? If I add 0, 1 to 0, 1, what do we get? 0, 0. 1, 0 to 1, 0 gives me 0, 0, right? Notice that when I add any element in Z2 to itself, I get the additive identity back again. Is that what happened over here? No. So even though I can label this, say, A, B, C, D, and label this A, B, C, D, no matter what I do, I can't make the tables match. All right? Because this would have A down the diagonal. This would have A, C down the diagonal. So they wouldn't be isomorphic. I can't reorganize it at all, right? So it's not enough to just be 1-to-1 and onto to be isomorphic. They have the same size. If it's 1-to-1 and onto, they have the same size. Even from an infinite perspective, they would have the same size. Okay. So there has to be something about the structure as well. Okay. So what has to happen? Well, if I have the same exact table, that means that if I do the operation in the first spot, it shouldn't matter if I do it in the second spot. So what I mean by that is I should be able to do the operation and then do the identification, or do the identifications first and then do the operation. And I should end up in the same spot. Okay? So, I said 3 properties. I guess technically there are 4 because I need to make sure they both work. All right. So 3 says that if I do the function on A plus B, that is, do the operation in the first ring and then identify the answer with something in the second ring. That should be the same thing as doing the identification first and then doing the operation in the second ring. It shouldn't matter if they are the same structure. It shouldn't matter where you do the operation. That's what this says. Okay. Now, since rings have 2 operations, I need to make sure that both operations are preserved. So the last one would be phi of A times B would be phi of A, phi of B. So at least another way that I like to think about isomorphism. It shouldn't matter what I call the elements, right? The operations should look identical as long as I know what's being called what, right? We all have a first and last name. Call us by our first names, call us by our last names. It shouldn't matter. We should still be the same people, right? So that's the same idea here. I can call it 0, 1, 2, 3, 4, 5 in the first ring, or I can call it 0, 0, 1, 0, 1, 1, 0, 2, and so on in the second ring. Doesn't matter. I still see the same structure in both places. That's the idea. Okay. All right, so here are the fancy words. By the way, all the fancy words assume that this is true. We have a function, okay? So that's given, right? If you don't have a well-defined function, then none of this matters afterward. Okay. These two together say we have a ring homomorphism, and we'll talk a little bit more about homomorphisms here in a little bit. If it's what we refer to this as operation preserving, okay? What I mean by that is, doesn't matter if you do the operation in the first ring or do the operation in the second ring, you get to the same place when you apply the function. Okay? That's operation preserving. Now, if I take homomorphism plus injective, so if you have a 1-to-1 homomorphism, that's referred to as a monomorphism. And then homomorphism plus surjective is called an epimorphism. Mono kind of makes sense. 1-to-1, mono, right? So the epi is on top of, lands on top of this. Okay, so sometimes people shorten homomorphism to just morphism. And so if you hear morphism, it means homomorphism means the operation is preserved. Okay. Splits up over sums, splits up over products. Okay. Later on, when we do groups, we will just have one operation, so it just needs to split up over whatever the operation happens to be. Okay. All right. Anyway, that's a long-winded definition. The idea again is the idea behind this is, as long as I have a well-defined identification, it should not matter where I do the operation. Okay, so in the first case with this example, we did the operation in Z6 and then mapped, versus the other one would be map and then do the operation in Z2 cross Z3. So I mean, from an algebraic perspective, there's something there, right? It matters where you start and where you end. All right. So obviously, well, maybe not so obvious, for heaven's sake. Will it respond or will I have to close it? I'm dead serious though. I teach all my classes on this same thing. It literally only does this in here. I don't know why. I have no idea why it only behaves badly. I mean, it must be you people. Well, it's not me because I'm always around it, right? So it can't be me.
Yes.
It's got to be Hope. She broke the light early. Okay. What's that? The only thing I know for certain is Hope's still around when it breaks. So. All right. So anyway, I mean, if you have a small enough ring, then you could just work with your tables each time and get to see whether or not it's isomorphic or not, right? But of course, the bigger the rings get, the more tedious that would be, which is why we do the function definitions to see if we can identify something. Okay. Of course, actually being able to identify whether something is an isomorphism or not can be difficult. Okay. So let's see if we can do some of these. This is, let's look at number 4 to start with here. So let's look at, let's first look at the ring S. That's just what looks like the even numbers that are in Z10. We've already dealt with that ring before. We've seen that it is a subring of Z10. It's not too hard to see that it's a subring. Okay. And let's look at, let's say, is S isomorphic to Z5? That's the question. Okay. Well, first, there are some things that you can look at quickly to see that things are not isomorphic to each other. For example, like what I did here on the board. Here, in this ring, everything added to itself was the identity. And I did not have that same quality here. Right? So they can't be isomorphic. Right? What I mean by that is, no matter where I identify 1 to go over here, this over here, 1 plus 1 is 2. It's the answer to wherever I put 2, right? But over here, it would be 0, wherever I put 0. And 0 would have to go to 0. We'll prove that here in a little bit. But generally speaking, these can't be isomorphic because 1 added to itself gives me 2, but nothing over here added to itself gives me something different than 0. Does that make sense? So if you can find something that happens in one ring that can't happen in the other, then you know they can't be isomorphic no matter how hard you try. So to give another example, if one ring is commutative and one ring is not, then they can't be isomorphic to each other. Right? Because no matter what I play with in the first ring, the elements would commute. But if I do it in the second ring, they may not commute. Okay. What else could you look for? Well, if they don't have the same size, that's pretty quick. You can't add a 1-to-1 onto function if they don't have the same size. Right? If it's 1-to-1 onto, they literally have to have the exact same size. Okay. So there are some things that tell you whether or not, there are some things you can look at that can tell you quickly if they're not isomorphic. Because again, remember, isomorphic means same structure. Well, one's commutative, one's not. They don't have the same structure. Right? Okay. None of that works here. Okay. In S and in Z5, they're both commutative, right? Their multiplications will commute, correct? I don't have anything that's going to add to itself and get back to identity in one and not the other. So this one's not that as quick to see whether or not they're isomorphic. Okay. So let me ask you this first. Does this identification work? I would say that this identification is probably the natural one, right? Double the number. That goes from Z5 to the set S. That's kind of the natural one, right? Z5 is 0, 1, 2, 3, 4. S is 0, 2, 4, 6, 8. That is certainly the way I've written that. And by the way, that's just a fancy notation to say the element 0 goes to 0, and that's why we put the little vertical bar on there. Okay. Element 0 goes to 0, 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. It's doubling, right? Does this work? Why not?
Because 2 times 2 equals 4. So what would be your multiplicative identity in 5 is not completely yes.
That's exactly right. So that second property of multiplication that we have, the second property of the isomorphism, if we have a function that satisfies those properties, we call it an isomorphism, because I didn't write that down. Probably easy to follow that from injective gives you homomorphism, surjective is epimorphism, so it's bijective gives you isomorphism. We have to satisfy both 3 and 4 to be an isomorphism, right? In particular, if I do 1 times 1 and then map it, it has to be the same thing as mapping 1 and then mapping 1 and multiplying it together, right? But phi of 1 times 1 is just phi of 1, which would be 2, like Devin said, right? Phi of 1 times phi of 1 would be 2 times 2, which is 4. That's not the same thing, right? So that would not work. Now, just because I found one function that did not work, does that mean they're not isomorphic? No, not necessarily, right? Just because I found one that didn't work doesn't mean there isn't one that does. Okay? But I said sometimes it's a little bit harder to find the isomorphism. Okay? So the whole reason why I'm doing this particular example, it's not an easy concept, right? If I want to show, it's a lot easier to show something's not isomorphic if they actually aren't isomorphic, right? Because I can find a property that one has that the other doesn't. Okay? It's a lot harder to show that something is isomorphic because the only way I can do that is to find the function that works. Okay? Now, there are some things that help us figure out that they do work. Okay. One, to tell us that this may not be a waste of time, does this function satisfy the property 3? Does it break up over sums? The way I have this written? What I'm asking is, if I do phi of x plus y, is that the same as phi of x plus phi of y? Not 4, it's a y. So again, the way we have this defined, it's doubling, right? On the left-hand side, this would be 2x plus y. On the right-hand side, this is 2x plus 2y. Are those the same thing? Yeah, in this particular ring, they are. So this does satisfy the third property. So at least from that perspective, the idea that looking for an isomorphism isn't a waste of time. Because I actually did find a function that preserves the first operation. Right? Okay? Now, that's not a guarantee either, by the way. But at least it's kind of an inkling that it may not be a waste of time. By the way, these two things, the way this works for this particular function, we did find an isomorphism of groups. It's just not an isomorphism of rings. Rings is a little bit more restrictive because I have to satisfy both operation preserving properties. Okay. We'll talk more about the group stuff later, but I just want to mention that this is an isomorphism for groups, but it's not for rings. All right. Now, again, this is no guarantee that I'm going to find an isomorphism. I'm just saying that at least I have something that shows the addition parts are isomorphic. They have the same addition structure. Okay? So at least it doesn't feel like it's a waste of time. Well, I don't feel like it's a waste of time. You may think this entire class is a waste of time. Okay? But at least from that perspective, it doesn't feel like it's a waste of time. Okay? It may still be. We may still be unlucky. Okay? But at least from this perspective, you know what? Maybe this isn't such a bad idea. All right.
Is it the same mapping for additional multiplication?
Say it again.
Do you have to maintain the same mapping for additional?
It has to be one function that preserves both. Yeah. Okay. All right. So let's think about let's think about two more properties to start with that isomorphisms have to have. One of which a homomorphism has to have, regardless. Okay. So, pardon me. So if we have phi of 0 for the first string, well, how can we rewrite 0? 0 plus 0, we've done that several times, right? Oops. And then since this is just homomorphism, by the way, this has nothing to do with isomorphism. If it's a homomorphism, it has to preserve the additive structure. So I can break it up, right? And now what can we do to both sides of that equation? Subtract phi of 0, right? Whatever that happens to be, right? If you subtract phi of 0 from both sides, you get 0 on one side and phi of 0 on the other. Now, I probably should have been a little bit more precise. If I have my function going from R to S, what is this the additive identity of, R or S? If phi goes from R to S, is that the additive identity of R or the additive identity of S, the one I pointed to with the arrow? R, right? That's an input, correct? Where is this one? S, yeah, it's the output, right? Okay. So, in particular, what does this say has to happen if you have a homomorphism?
The zeros have to map onto it.
Yep. The additive identity of your domain has to be the same as the additive identity of the image, the codomain. Okay? Pardon me. Over on the other one, if we want to do the phi of the identity, we have to be a little bit careful because, well, for lots of things. If it's not one-to-one, I don't necessarily know that I map onto the multiplicative identity of the codomain piece. However, we do have to have that this is the identity if your function is onto. We can be a little bit more precise. You have done range in algebra class before, the set of all possible outputs. We can define a similar thing with functions in algebra, and in particular, homomorphisms in algebra. If I talk about the image of a homomorphism, the image is just a set of all outputs. It's like the range. So take anything in the domain, which I'm using as R, right? I'm thinking of phi is going from R to S. I just plug everything in from R, get everything out in S, make a collection. That's the image. Okay. All right. So it turns out that phi of 1, no matter what it is, whether it's onto or not, phi of 1 has to be the identity in the image. It just doesn't have to be the identity of the codomain. If you're not on 2, you might have a smaller image than you had for the whole ring. A phi of 1 still has to be the identity for the image. Okay. So what I mean by that is, if we let y be in the image, to be in the image, that means there exists something in the domain such that when I apply the function to it, I'm using, why am I using f? Sorry. Why am I using an f? F'd that up. Not an f, it's a phi. It's the image of phi. I'm talking about a function phi. Sorry about that. Good grief. Anyway, if it's in the image, something in the domain got mapped to it, right? That's what it means to be in the image. There's something in the domain that gets mapped to that element, right? I want to show that phi of 1 is the identity of the image. That's the idea here, right? I'm not saying that it has to be the identity of the codomain, but it does have to be the identity of the image. Okay? Well, what can we replace y with? Phi of x. Oops. Now it's using the second property in reverse. It looks like we've already pulled it apart, so we can put it together. Good. Phi of 1 times x is, well, what's 1 times x going to be? X. And phi of x, another name for that is y. Yeah. So the whole point of this was to show that phi of 1 acts like the identity of the image, right? Well, if it's 1 to 1, or excuse me, if it's on 2, that means the identity had to get hit by something, right? And there's only one identity in any ring. There's only one multiplicative identity, period. So if it's on 2, phi of 1 has to equal 1. Okay. So the important part of this is, out of all of this, and I know I didn't do a very good job explaining it, which happens from time to time. It's a hazard of the job. Okay. When you map the identity, it goes to the identity, but not necessarily of the codomain, is what I mean. Okay? It has to go to the identity of the image. Okay? So let's go back up to what we were talking about. Rather than going back up, I'll just rewrite it. Using the 2 things that we just talked about. Where's a 5? I don't see a 5. All right. Using the first property that we just talked about, where does 0 have to go to? 0, okay? Definitely these 2 things have to match each other, without a doubt, right? But what I need to know is, where does 1 go, right? So I need to see if I can figure out what the multiplicative, if they're going to be isomorphic, I need to figure out where 1 goes, right? Well, we just established it's not 2, right? So you only have 3 more choices to check. Which of these things is the identity? Well, let's square them all and see what we get first. Square 2, you get 4, doesn't work. Square 4, you get 6, that doesn't work. Square 6, you get 6. Square 8, you get 4. So the only possibility that you can get for the identity is 6, right? So if it's going to work, 1 has to get mapped to 6. If it's going to work, right? That was what we just established, isn't it? if S is going to be the image, one has to get to map to the multiplicative identity of S. The only thing that can possibly be the multiplicative identity of S is 6. It's the only thing that can possibly work, right? Everything else, when you square it, you got something different than itself. Does that make sense what I'm saying? Okay. So does the rest of this work? Well, let's see what has to happen. Let's see if we can generate the rest of them. Okay. So we just said phi of 0 would be 0. Phi of 1 would be 6. How can we figure out where phi of 2 goes?
6 plus 6.
6 plus 6, good. Which is 2. Because we're doing everything mod 10. So it's just dropping the tens digit off. Phi of 3. Yep, how'd you get 8?
2 plus 6.
Yeah. The last one better be what if it's going to work? Better be 4, right? Because it has to be 1 to 1, right? I can't get a different answer. It better be 4 if it's going to work. And it's equal to 8 plus 6, which is 4. Now, did we prove this really was an isomorphism so far? Or did we just show that it would work for addition? I didn't show that it's operation preserving for multiplication, did I? Okay. All right, so, but let's see if we can figure out what the rule is, and maybe we can show operation preserving for the rule rather than trying to do this piece by piece every single time, okay? So what is the rule? Well, 1 got mapped to 6, 2 got mapped to 12, but we can think of that as this is the same thing as 2 times phi of 1, isn't it? You agree with that? This is the same thing as 3 times phi of 1. This is the same thing as 4 times phi of 1. What was phi of 1? 6, right? So it looks like phi of x should get mapped to 6x, right? This is 6 times 2, 6 times 3, 6 times 4. That makes things a little bit easier to check preserving of things, doesn't it? Because now, if I want to do operation preserving, if you do phi of x plus y, that's 6 times x plus y. Distribute the 6 and see that the addition is preserved. Let's do it this way for this one. What would be phi of x times phi of y? By definition, what would it have to be? Just by the definition of phi, I mean, what would it have to be? 6 times x times what? 6 times y, right? Now again, where is the operation taking place when we do 6x times 6y? What ring is that taking place in? The S, which is a subset of Z1 10, right? So everything's going to be mod 10, right? So you do your 6 times 6, what are you going to end up with? 6, yeah. So this will be 6xy, because 36 is 6 mod 10, right? And so this will be phi of xy. So this is what I meant by, if we can find a rule for the function, it's a lot easier to determine if it's operation preserving or not. That okay? All right. We did a lot of work on that one particular example, and it was number 4 in the homework. But let's talk about why we spent so much time on it. Number 1, we got a couple of properties that homomorphisms have to satisfy, right? The 0 of your domain always has to go to the 0 of the codomain, no matter what. Homomorphism, monomorphism, epimorphism, isomorphism. No matter what, 0 has to go to 0. Okay? Period. The end. Okay? Second property we proved was if there's a multiplicative identity for your domain, it has to be the multiplicative identity of the codomain as a subring. May not be the identity of the entire codomain. It would be if it's onto. Okay. The third thing that we did with all of this work, we showed that there's exactly one isomorphism. There's only one. That's all we get. Okay? All right. Let's do another example along those lines. Let's say we have, this is number 8. Yes. Adjoined something. So this is what we typically say as Q adjoin the square root of 2. Yeah, strange word. Q adjoin the square root of 2. So we think of them as polynomials in root 2. So remember we use the bracket and put an X in it, that meant the set of all polynomials. But notice that if I do polynomials in root 2, when you square root 2, you just get back to a rational number again. So I can write everything in as that. Okay. So Q is a field, right? Everything has a multiplicative inverse. Q adjoin root 2 also is a field. You can show that it's a field. It's a little bit more work, but it's not too bad. You have to use conjugate kind of ideas to get to it. Okay. But notice that it's properly bigger than Q, right? Square root of 2 is not rational, so this is a bigger thing. So Q would be a subfield of this. So we had subring, right? But field's a little bit more strict, if you will. So this is a subfield of that. So what we want to do is we're going to look at a function from this ring to itself. And we're going to define it by taking a plus b root 2 to the element a minus b root 2, taking it to its conjugate. And we're going to show that this really is an isomorphism. Since it's going from a ring to itself, an isomorphism from a ring to itself or from a group to itself is called an automorphism. I know, more words today. So an isomorphism where the domain and codomain are the same is called an automorphism. All right, so to show that this is an isomorphism, we need it well-defined. I need a well-defined function. Well, if I had two different things, or if I put the same thing in, I would have to get the same thing out, right? Because if a plus b root 2 is the same thing as c plus d root 2, then the a and the c are the same, the b and the d are the same, and you get the same output. That's what we mean by well-defined. Usually well-defined only comes up if you are trying to define a function dependent on its representation. Remember I mentioned that the other day, that if you have a function, and I said over of some rational number as r over s, and you said you wanted to make that equal to r, that causes a problem if R over S isn't in lowest terms. Right? You might get different answers. Because that depends on the representation of the fraction that you took. This would not be a well-defined function unless I knew for certain this was in lowest terms. Okay, that's what I mean by well-defined. We're going to come back to that idea. Everything comes back later in the semester. I keep saying that, right? All right. Anyway, this is well-defined. We want to show one-to-one. So to show one-to-one, remember again, you assume you have two outputs of the same. Sorry, outputs. Try that again. If I want to, what should I end up with when I'm done if it's going to be one-to-one? If I start with outputs that are the same, what should happen? Inputs are the same, right? So if I start with phi of A plus B root 2 equals phi of C plus D root 2, our very last line better be what? If I start with f of x equals f of y, my last line needs to be, for showing one-to-one, x is equal to y, right? So my very last line should be a plus b root 2 equals c plus d root 2. So that'd be one-to-one, right? Okay. All right. So according to the definition of the function, we would need a minus b root 2 equals c minus d root 2. If those two things are going to be equal, what has to be true? Yeah, so the AS equals C, and then the coefficients of the root 2 have to match, right? So technically right now I'd have the negative D equals negative D. Drop the negatives off, and then put the pieces back together. So that shows it's injective, shows it's one-to-one. This is pretty standard for functions in general, right? Take two outputs, assume they're equal, show that the inputs have to be equal. Pretty standard one-to-one proof. We will have another way to show something as one-to-one later on in the semester. All right, let's do onto. Onto, you need to show start with an arbitrary element in the codomain and show there's an element in the domain that gets mapped to it, right? So we'll start with, I'll just write it as C plus D root 2 for whatever reason. That's an arbitrary element of the codomain. What thing in the domain will get mapped to that element under this function? What thing should we pick in the domain to map to it? Well, it usually is going to be in terms of whatever element we picked.
No.
So my mapping is this one, right? So to end up with a C plus, oops, my D went bye-bye. To end up with C plus D root 2, what do you need to plug into that function? Yeah. Is that an element of Q root 2? Is that an element of the domain? Yeah. So again, to show something is onto, start with an arbitrary element in the codomain. In this case, the codomain is the same as the domain, but start with an arbitrary element of the codomain and find something in the domain that when you plug it into the function, gives you the thing you started with. Okay. Notice for both one-to-one and onto, when you do your proofs typically, they both start in the codomain, right? In the first case, for one-to-one, we assumed that the outputs were equal and got to the inputs are equal. For the onto, we started with an element of the codomain and found something in the domain to plug into the function. Okay. So in both cases, you're starting in the codomain space, the output space, the output ring in this case. Okay. Let's do one more. We got time. Oh, wait, I'm not done with this one. I didn't finish this off. I didn't do operation preserving, right? I usually denote or abbreviate operation preserving as OP. All right, so remember for rings, we have to show that both operations are preserved by the function. So I need to do phi of two things added together, and I need to do phi of two things multiplied together. I got to do both. Okay? You'll like groups later, we only do it one time. Rings, we have to do it twice. Okay? All right. Notice I wrote it this way. I did phi of x plus y, essentially, to start with. Usually it's easier to break things apart than put things together, generally speaking. For it's backwards. Usually we think about it, usually it's easier to put things together than break things apart. Think about factoring, right? But for homomorphisms, it's usually easier to do it this way. Okay. All right, so notice that I have to add and then apply the function, right? So we add like terms, essentially, right? We get a plus c plus b plus d root 2. When we apply the function to that, what do we get? What's the function do to the input? Scroll back up. What's the function do to the input?
Subtracts the whatever times root 2.
Yeah, so it just does the conjugate, right? Just flips the sign in the middle. So what is this output going to equal?
A plus C minus B plus D.
Good. Now what do you think we might want to do? We're trying to get to phi of a plus b root 2 plus phi of c plus d root 2. So what do you think we want to do now? Good. Yeah, rearrange it a little bit, right? And now that first piece is phi of a plus b root 2, and the second piece is phi of c plus d root 2. That's not supposed to be on there. Okay, there it went. That okay? Okay. Do it the other way, or do it for the other operation. I'll do this quickly since we got about a minute. When you multiply these together, you should get AC plus 2BD, and then plus AD plus BC root 2. So when you multiply them and recombine, then when you multiply your root 2 pieces together, a 2 will pop out. So that'll be your real or your rational part. The function flips the sign in the middle. You can check. This might even, oh, for heaven's sake. Hang on. Microsoft will report the problem. Fat load of good it does. Okay. Anyway, you can, well, that erased my whole thing. Great. Let me get back to where we were. You can check that if you multiply A minus B root 2 and C minus D root 2, you really do get that. It's not too hard to check. Or you can do a meet in the middle approach. Right? What I mean by is, it's not going to scroll again. It's going to die again. What I mean by that is compute your phi of A plus B root 2 and your phi of C plus D root 2, and see you get that. And that's what I mean by meet in the middle. Compute one, compute the other, show they're the same. All right, sorry, I got this. You kept you a minute late. We'll do more examples like this. Hopefully it'll start to make a little bit more sense. I won't assign anything new. Unless you really want some homework.
No?
No? You're good?